Hello everybody, Dr. D again here. This is our second video, chapter 11, and this chapter is properties of solutions. And specifically, we're talking here a lot about what we call colligative properties. And colligative properties are properties that do not depend on the nature of the particles in the solution, but only on the numbers. Okay, the identity of the particles is irrelevant. Similar to ideal gases, how we said it didn't matter. We can use the ideal gas equation for nitrogen gas, or we can use it for, carbon dioxide gas. It doesn't matter. You can calculate the pressure the same way. The identity of the gas is irrelevant as long as they behave ideally. And it's the same with the solutions here. As long as these solutions are behaving ideally, it doesn't matter whether the solution has sodium chloride or potassium chloride. It's the number of particles that matter, right? And if they're at the same concentration, they have the same number of particles, therefore it doesn't matter what the identity of those particles are. And the types of things that we'll be talking about here then are things like osmosis, things like vapor pressure, the volatility of substances, right? And then, melting point and boiling point, stuff like that. These are properties that depend only on the numbers of particles, not on the identity of those particles. Hence, they're known as colligative properties. And the first thing your book talks about is osmosis. So I want to talk about osmosis a little bit right here. Let's imagine we have this chamber filled with a solution of water, let's say, and it's separated by a semi-permeable membrane. Okay, and a semi-permeable membrane, these semi-permeable membranes means they're permeable to water, but they're not permeable to ions and molecules and other stuff dissolved in the water. Okay, now that might seem a little confusing because you say to yourself, well, wait a second, Dr. D, if I have something like sodium chloride dissolved in solution, I have a sodium ion, and comparing that to a water molecule that has 3 atoms. Sodium cation is only 1 atom. So certainly the water molecule must be bigger. How can the water molecule pass through this membrane? Because basically it's just a bunch of pores in this membrane, specialized membrane, that allows small particles through but not large ones. Well, you got to recall what we learned in chapter 6, that particles like this are not naked, they're not bare, they have a sphere of hydration. They're surrounded by a bunch of water molecules, remember. And they can have multiple spheres of hydration. So it's going to be surrounded by at least 6 waters, which makes it much larger than a water molecule. So now water can move freely in between the semi-permeable membrane, but anything else in solution cannot. Okay? And even if you take something that isn't necessarily attracted to waters, it's still going to be larger for the most part than waters. Things like methane gas, which can have, 5 atoms compared to water's 3. So, because remember, and this is what's unique about water, it's a solvent. I mean, it's a liquid at room temperature. Most things with molecular weights as small as water are gases at room temperature. Okay, so let's now add a substance to this. So we're talking about osmosis now. Let's add a substance here. Whatever, it could be sodium chloride ions. Now, realize that water can move in both directions, of course, but the net movement of water would be in this direction. So that would be the net. So, if you will, you have a bunch of water moving in this direction, a small amount moving in this direction, the net movement is in that direction. So, the way to look at it is the net movement is from the region of a high concentration of water to low concentration of water, or a low concentration of ions to a high concentration of ions. The way I like to think about it is that, we're trying to dilute this side over here so that the two sides are more comparable in concentration. Now, it's difficult for me to explain this right now because 2 of the major concepts that we need to explain this we haven't covered yet. One is entropy, which I can't go into now, which we'll go into later. The other is kinetics, and you can see that here, that the water's moving in both directions. It's just that because some of the movement in this direction is taken up by particles hitting the membrane and not getting through. So if you will, some of those collisions are not water molecules. Well, all the ones in this direction are water molecules, which you can pass through. that will have a net movement from left to right. And that's what osmosis is. Now, when you have osmosis going on, what happens is you have a pressure buildup. So if you think of it like this, let's imagine that this chamber is actually much larger up top. And there's a picture in your book. I should have left that in here to use this here. Let's say that that chamber goes up higher here on both sides, but that's the water level. So as water moves in this direction, I'm going to use a different color. As water moves in this direction, obviously the water level is going to rise here. It's going to drop here. So ultimately, it's going to be down at this level here and this level here. You reach a certain point where you can imagine this now, it's going to have to stop, right? You can't just have all the water move until it's all dry over here. Why? Because there's an opposing force going on here, right? If you've taken physics, you know that gravity. That this water column now is subject to greater force due to gravity than this one over here, because it's the mass times acceleration, right? Force is mass times acceleration. The acceleration is the same, g, but the mass of the water on the right now is great. So you reach a point at which this balances, and that is the force driving water in this direction is balanced by the force of gravity pulling it down. That difference in height here is your osmotic pressure. Okay? That difference in height there is your osmotic pressure. And that can be calculated. There's an equation in your book. You're not responsible for calculations based on osmotic pressure. You see that based on the outline and based on the questions I've assigned to you. So this also explains why you can't drink salt water. If you're stuck at sea, it's stranded at sea, you die of dehydration. Die of hydration. What happens is, if this is your red blood vessels, right, your red blood cells, if you drink a bunch of salt water, because the salt concentration now that's going to be outside these blood vessels is greater than what is it inside, all the water from inside the cell moves outward due to osmosis. And your cells will shrivel up and die. So you're better off not drinking than drinking salt water. Okay? And we'll talk more about that in class. So I did have a blank slide here for drawing all this. I forgot. But that's osmosis. Now let's talk about, so once again, the osmotic pressure does not depend on the type of particles, just the numbers of particles. And you can see that from the equation in your book. The actual concentration, the molarity will be important in getting your osmotic pressure. Now, vapor pressure. What is vapor pressure? The correct name is equilibrium vapor pressure. And it's the pressure that's exerted by the gas above a liquid in which the two phases are in equilibrium. The gas and the liquid are in equilibrium. So we got a piece of styrofoam over our glass here, because obviously if we don't have that styrofoam there, or a lid of some sort, the water vapor is just going to evaporate into the room and dissipate into the room, and then slowly that water will just completely evaporate and you'll be nothing left with some salt at the bottom of your glass over time. So we have to have a lid on it. And that's why we call it equilibrium vapor pressure, because you see here, that just means the forward and reverse rates are the same. The rate of evaporation and the rate of condensation are the same. Both are happening. Equilibrium is a dynamic system. We'll talk about equilibrium a lot this semester. And both of those are happening, but just at the same rate. Well, the pressure that's in here, when this system's in equilibrium, that is your vapor pressure. And any substance that's considered volatile will have a high equilibrium vapor pressure. There'll be a bunch up here if it's a very volatile substance. Something like gasoline, right? You can smell it, so you know there's a bunch in the air, right? Or certain substances you can't smell because they're not very volatile. So the more volatile it is, the greater the equilibrium vapor pressure is going to be. Now, I can mix two volatile substances, right? And how might you visualize calculating that vapor pressure if I had a mixture of two substances? Well, you'd want to know what each substance is, right? And each of those substances will have a vapor pressure. We'll just call it P naught, or you can even call it P naught 1 and P naught 2 for the two different substances. That's their vapor pressure. But we want to know what amount of each of those is in the mixture, because that's going to determine how much is in, right, the vapor phase. So we use a mole fraction. You'll see that in your book like this. You add these two together with the 2 mole fractions, you get the total vapor pressure, and that's not the same notation used in your book, I don't think. The total vapor pressure of that mixture of solutions. That mixture, which is two substances mixed together to form a solution. They have to both be, we're talking about 2 volatile substances here, okay? It just should make sense to you that, you know, if you got 2 substances, the more volatile one will contribute more to that pressure if they're in equal amounts. So if the mole fraction of each of these was 0.5, 1/2, you know, then the one that's more volatile, has a greater vapor pressure, will contribute more to that vapor phase. That shouldn't be surprising to you. Now, what if I take a volatile substance and add a non-volatile substance? So the idea here is now I've added something that's not volatile. How does that affect it? Well, I got some particles here, and actually, because of those particles here, they also represent particles at the surface, right? It makes it more difficult for the volatile substance to escape. So the vapor pressure is lowered. We call this vapor pressure lowering. Because that non-volatile substance is taking up space for that material to be able to volatilize. There's other ways to explaining it too, that they might interact in solution to some extent and therefore not volatilize, but that gets away from ideality too. So for the most part, just think of it as these particles are taking up space, and therefore it's more difficult for the volatile substance to volatilize. So we call that vapor pressure lowering. Now, one thing we see is boiling point elevation and freezing point depression. That is, the boiling point of a substance increases and the freezing point decreases when we add these substances to a solution. So if I add something like salt to water, its boiling point is increased and its freezing point is depressed. Okay? And we'll talk about that in the classroom. But what boiling point is, normal boiling point, is the temperature at which the vapor pressure is equal to the atmospheric pressure. So what that means is the normal boiling point of water is 100 degrees C. At 100 degrees C, that means the pressure of water above its liquid phase, if we had a sealed container, would be 1 atmosphere. And that's equal to normal atmospheric pressure at sea level. That's what happens when those two pressures are equal. That's when you get volatilization of the substance from the entire liquid, not just the surface. Evaporation just occurs from the surface. Once you reach the boiling point, it's literally like saying, okay, it's now evaporating from the interior of the liquid, and that's what the bubbles are that forming. So boiling point is the temperature at which the vapor pressure equals the atmospheric pressure. If it's normal boiling point, then we say it's 1 atmosphere. And you could say the same thing about freezing point. Normal, 1 atmosphere. And keep in mind that freezing point and melting point are the same thing, just kind of the direction you're thinking about it. And boiling point and condensation point are the same thing. And of course, you can also have sublimation deposition. And that is a solid going directly to gas and a gas going directly to solid. And we'll see that. Or we've actually seen it with carbon dioxide in Chapter 6. At certain temperatures and pressures of carbon dioxide, normal temperature and pressure, it goes directly from a solid to a gas. So in order to calculate, we're going to be able to calculate the amount of the boiling point elevation and the amount of freezing point depression or decreasing. We need to be able to use molality. That's molality with an L as opposed to molarity. And the difference is it's still moles of solute, but it's kilograms of solvent. Remember, molarity with a capital M was liters of solution. So it was the total solution amount. With molarity, it's only the amount of solvent, and it's the mass of the solvent, not the volume. Okay, so we'll do some molality calculations, and then we'll use it to calculate things like vapor pressure and, freezing point depression and boiling point elevation. With that, that concludes my video for Chapter 11.